Okay, take a look at the text in front of you. At first glance, absolute gibberish, right? Just a complete mess of jumbled letters. But watch what happens as you read it. According to a research at Cambridge University, you're probably reading it without a hitch. It's actually kind of wild. This right here perfectly demonstrates the incredible ability of the human brain to just instantly extract patterns from pure chaos as long as the first and last letters are in the right place. See, our minds don't read every single letter by itself. We process the word as a whole.
So that brings us to a really fundamental question. What exactly is intelligence? And how in the world does our biological brain pull off these instantaneous acts of pattern recognition? But more importantly for our technological future, how do we even begin to attempt recreating these incredibly complex biological processes artificially?
Well, welcome to this explainer. Today, we are demystifying artificial intelligence by tracking it all the way back to its biological roots. I am so excited to guide you through this fascinating journey of how human biology literally inspired the greatest technological revolution of our time.
Okay, let's dive into this. Here's our roadmap for today. First up, the nature of intelligence, then defining AI, contrasting strong and weak AI, looking at a brief history, real-world applications, and finally, the very first neural model.
Section 1. The nature of intelligence, moving beyond human capability.
To truly get a handle on intelligence, we actually have to step outside of our own human experience for a second. Meet our test subject. This is a pigeon inside a 1995 Skinner box. Now, researchers wanted to see if they could train these birds to become, well, fine art critics? No, seriously. They presented the pigeon with paintings by two very different artists, and the pigeon was rewarded with food only for pecking a button when a specific artist's work was shown.
Now, what's really interesting about this is the artists they chose, Marc Chagall and Vincent van Gogh. The results? Absolutely fascinating. The pigeons were able to discriminate between the Van Gogh and Chagall paintings with a staggering 95% accuracy for the pictures they were trained on. But here is where it gets totally mind-blowing. When they were presented with completely unseen, brand-new paintings by these same artists, their discrimination was still 85% successful. I mean, wow.
And that brilliantly illustrates our core definition of intelligence. See, those pigeons weren't just memorizing pictures, their tiny little brains were successfully extracting and recognizing complex patterns. They were recognizing an artist's abstract style. So, intelligence is exactly this. It's the ability to extract patterns, generalize from what you've already seen to make predictions and solve ambiguous problems. This biological ability to extract patterns, that's exactly what artificial neural networks are designed to emulate.
Section 2. Defining artificial intelligence, replicating biological processes.
So how exactly have we humans attempted to artificially recreate the problem-solving abilities we just saw in human readers and, art critic pigeons? Well, in the academic world, views on AI generally fall into four distinct categories. You can map them out across a matrix of thinking versus acting, and doing so humanly versus rationally. For instance, thinking humanly is all about getting inside the actual workings of the human mind, while thinking rationally is about the strict, rigid automation of logical decision-making. But arguably the most famous benchmark for AI sits squarely in that acting humanly category. I am talking, of course, about the Turing test, proposed by the legendary Alan Turing back in 1950. The setup is elegantly simple, yet deeply profound. A human interrogator types questions to two unseen entities. One is a real person, and the other is an AI system. If the AI can successfully trick the interrogator into thinking it's the human, boom, it passes the test for intelligent behavior. It is the ultimate test of acting humanly. But, to pass this test, a computer system can't just rely on a few cheap party tricks. It actually must master a massive array of capabilities. It needs natural language processing just to communicate, knowledge representation to store what it learns, automated reasoning to draw conclusions, and machine learning to detect patterns and adapt on the fly. And if the test involves a physical environment, well, then add computer vision and robotics to the list. It literally requires an entire symphony of artificial disciplines working together in harmony.
Section 3. Strong versus weak AI. Understanding current limitations and methodologies.
Now, when we talk about all those incredible capabilities, we do need a bit of a reality check. As you probably know, we have to separate strong AI from weak AI. Strong AI, that's the sci-fi dream. We're talking about a conscious, human-like mind, a computer with enough processing power that it can literally think. But weak AI, which is the practical, applied modeling of intelligent behavior to solve specific, complex problems without proving actual consciousness. That's where the real work happens. In fact, everything we interact with today is weak AI.
Understanding how these systems actually solve problems comes down to strong and weak methods. Weak methods are general logic structures, things like automated reasoning, that can be applied really broadly without knowing a thing about the real world. Strong methods, on the other hand, rely on feeding the system a massive amount of specific knowledge about a problem's world. So the crucial point here is that a system with vast knowledge is actually completely useless without the underlying weak method logic to process it. They really have to work together.
Sections 4 and 5, History and Applications, from theory to our living rooms now.
All right, we've talked a lot about theory, so let's quickly map out how these concepts actually evolved over time. The acceleration of this technology is just staggering. In 1950, the Turing test was established, right? And the term artificial intelligence wasn't even coined until 1956. For decades, it was mostly just theoretical. But look at this timeline. From theoretical whiteboards in the 50s to IBM's Deep Blue defeating Garry Kasparov in 1997, to a Roomba intelligently navigating your living room in 2002, and then Alexa sitting on your kitchen counter in 2014. The gap between abstract theory and daily consumer reality is shrinking incredibly fast.
Today, AI applications are deeply specialized. Take a look at Cogni, for example. It operates as a virtual teaching assistant for the education industry. While your basic phone assistant uses shallow processing just for quick weather updates, highly specialized applications like Cogni use deep natural language processing to grade nuanced educational essays. We're training machines to actually comprehend context, not just hunt for keywords. It is an absolutely incredible example of applying advanced pattern recognition to human language.
Section 6, the first neural model, returning to the biological blueprint.
Let's move to and see how this all builds up. To truly appreciate how we arrived at conversational virtual assistants, we have to look back at the very foundation of machine learning. 7 years before the Turing test, way back in 1943, mankind achieved a quiet but totally monumental breakthrough. I'm talking about the McCullough-Pitts neural model. This was the absolute first time anyone successfully created a mathematical model of a biological neuron. They looked at how actual brain cells fire based on stimuli and translated that breathtaking complexity into pure math.
And the sheer beauty of this model was its powerful simplicity. By using mathematical weights and thresholds to simulate whether a neuron fires or doesn't fire, the McCullough-Pitts model successfully replicated fundamental logical operations. It could replicate an AND operation, an OR operation, a NOT operation, and an XOR operation. This was the spark. This proved once and for all that the logical reasoning our biological brains perform could be mapped out and automated mathematically.
Which brings us right to the edge of tomorrow. From pigeons recognizing Van Gogh to artificial neurons processing logic gates, we've spent the last 80 years aggressively scaling up the mathematical blueprint of our own biology. So, I'll leave you with this thought to chew on. If a shockingly simple mathematical model built way back in 1943 could successfully replicate the basic building blocks of biological logic, what are the ultimate limits of the massively complex artificial intelligence networks we're building today? Something to think about. Thank you so much for joining me on this explainer, and keep exploring.